Hello, today we're going to look at space-time and a thing called the twins paradox. And as usual, we're going to start at the very beginning. So the question is, what is space-time? Well, first let's ask ourselves, what is space? Space as we understand it is three-dimensional. That at least is what we observe. That means to say that in any area of space you can go left and right, or up and down, or back and forth. Three dimensions, and we usually represent that by three dimensions of space, or three coordinates of space, which we often label x, y, and z. And that is space. We now need to add to that time, and that's a fourth dimension. But it's very difficult to draw a picture with four dimensions. In fact, it's nigh on impossible. And even three dimensions can be rather confusing. So let's try and keep it simple. And we're just going to think of one dimension of time and one dimension of space. So it will look like this. Time we're going to draw upwards, and space we're going to draw as the x-axis. We'll forget about y and z for the moment, just to keep things simple. So time goes up and space goes along the x-axis. And that is essentially a picture of space-time. Now let's compare the two. If I stand still in space, then my coordinates do not change. I do not move along the x-axis or the y-axis or the z-axis. I stand still, and therefore that point doesn't change. But if I stand still in space-time, then although my space dimension doesn't change, I stay here on the x-axis, of course time is passing by relentlessly, and so in space-time I move in that direction, because although I'm not moving in space, I am moving in time. If you stand still in the middle of a room, time is nonetheless ticking by. Now there are some rules about space-time. For a start, you can't go backwards in time. So if we take our space-time chart, any movement like that is forbidden, because although it implies that you are moving to the left in space, it also suggests you're going backwards in time, and there is no known mechanism for doing that. Although there are some theories that suggest you might be able to find some kind of hole that enables you to go back to some point in the past, there is no known mechanism for doing that. And so you can't have any movement through space-time which involves going backwards in time. Now space-time charts are usually drawn in such a way, here's time, here's space, in such a way that the speed of light is drawn at an angle of 45 degrees. And the way you do that is you just make sure that the coordinates are appropriate. So for example, time might be 1 year and the space might be 1 light year, which is the distance light travels in a year. So light travels 1 light year in 1 year. And that's how you organise the chart. Or you could, for example, have time at 1 second and distance 3 times 10 to the 8th metres, because light travels at 3 times 10 to the 8th metres per second. So we usually arrange it, just for presentational purposes, so that the speed of light is at 45 degrees. Now, here's another rule then about our space-time chart. Here's the chart, time versus space. And now you cannot have any kind of motion that goes faster than the speed of light. So for example, something that goes like that is going faster than the speed of light. It suggests it's getting somewhere faster than light could, and you therefore cannot do it. So that is not allowed. Not only are you not allowed to go backwards in time, you're not allowed to exceed the speed of light. Now what that means is that there are limits of space-time of what you can experience. Let me explain. Here once again is our space-time chart, and here's the speed of light. And you cannot move in this direction. None of this area here is completely outside your limits. You can go like that, which means you're moving in space and you're moving in time and you're moving at less than the speed of light. But if you start from here, point X, you can never get to here, point Y. That is rather like saying that if you're in London now, can you be in New York in 5 minutes' time? The answer is no, it's physically impossible. It doesn't mean you can never get to New York, it just means you can't get to New York in 5 minutes. So yes, you can certainly get to this position. Here, for example, that's the same position, but at a later time. In other words, you can only get there if you travel less than the speed of light. And now we're going to use these charts to examine what is called the twin paradox. Imagine that this is the Earth, on which there are two twins. And let's imagine they've both just been born. And here comes a space rocket, which is travelling at speed v. And v is 3/5 of the speed of light. And it just so happens that this rocket has a little hook underneath it. And as it goes past at 3/5 the speed of light, it picks up one of these twins and carries it along at 3/5 the speed of light for a period of 5 years. Now, if it is travelling for 5 years at 3/5 of the speed of light, it will travel a total distance of 3 light years. Now, when it's travelled that distance, 3 light years in 5 years, it meets another spacecraft coming the other way, also at speed v equals 3/5 c. And that spacecraft also has a hook on it. And as it passes this spacecraft, it grabs hold of the twin and brings the twin back. And that will also take 5 years for the return journey. And as it passes the Earth, it releases the hook and the twin falls back down next to its brother, and they are reunited after 10 years. And you might think that they could together celebrate their 10th birthdays each. But as we will see, that is not the case. So let's start by drawing a very rough space-time diagram just to show what's going on, and then we'll do it slightly more accurately so that we can understand. What is happening is that the first twin, the one that remains on Earth throughout, will start at the year 0 and stay still basically up to year 10. And so the first twin doesn't move along the space axis at all, just stays still on the Earth. We'll imagine for the moment that the Earth is not moving, and so the space-time direction for this twin is straight up. They do not move through space, they just move steadily through time for a period of 10 years. Now the other twin is picked up by this spacecraft and is whizzed out to this point here, and then the second spacecraft, the return spacecraft, picks them up and brings them back here. And the total distance that they travel is 3 light years. So just to recap, twin number 1 stays still on the Earth and just travels through time for 10 years. Twin number 2 travels at 3/5 the speed of light to this point, outwards, 3 light years, and then travels back at 3/5 the speed of light and rejoins their twin on Earth. Now, what has actually happened? In my video on special relativity, I explained that a moving clock appears to run slow. And I'm just going to explain that again here so that we get the full picture. I said that you could invent a very simple clock. It would consist of 2 mirrors. And what you do is you simply bounce light up and down between the two mirrors. And every time the light beam hits a mirror, it essentially causes a counter to move on. And since the distance is known, and since the speed of light is invariant, we know that the time to travel from the bottom mirror to the top mirror is going to be the distance, d, divided by c, the speed of light. And that becomes, in a sense, our time measure. One movement from the bottom mirror to the top mirror constitutes a time interval which equals d divided by c. Now, suppose that apparatus is in a rocket that is going past the Earth. So here's the Earth with an observer on the Earth. And here's the rocket. And here's the mirror in the rocket. Now, the rocket is moving at velocity v, and for these purposes v will have to be pretty fast, approaching the speed of light, maybe half the speed or 3/5 the speed of light. So what happens? The light leaves the bottom mirror on its way up to the top mirror. But before it gets there, the rocket has moved, so that by the time it gets to the top mirror, that top mirror is now here inside the rocket. And then it's reflected, but by the time it gets to the bottom mirror, the rocket has moved to here. And there's the bottom mirror. So to the observer on the Earth, what the light beam has appeared to do is not gone up and down, but gone like that. So how do the two observers, one of them inside the rocket and one of them on the Earth, compare these two events? Well, the person inside the rocket says the light simply went up like that. The person on the Earth says, no, it didn't. It went like that. Now we can do some geometry. What we're going to do is we're going to create a right-angled triangle. This is distance d. That was the distance we had here. This is going to be distance, we're going to call it d prime. And of course this is also distance d. What is this distance here? Well, it's the velocity of the rocket, which is v, times the time it took to get from here to here, which we're going to call t prime. It's the time which the observer on the Earth will reckon that the rocket took to get from here to here. Well, now we can do some basic Pythagoras. D prime squared equals the sum of the squares on the other two sides, which is d squared plus vt prime all squared. But if it takes t prime for the rocket to get from here to here, then it also takes t prime for light to get from here to here. And that means that d prime is simply c times t prime. Now we can write that d prime squared is ct prime all squared equals d squared. Well, we calculated d. d is c times t. So d squared is ct all squared plus vt prime all squared. Now we can say that ct squared, bringing this on this side, equals ct prime squared minus vt prime all squared. All we've done essentially is to take the vt prime all squared onto the other side and just switch it around. So it's now ct squared equals ct prime squared minus, because we've taken it onto the other side, minus vt prime squared. Okay, so let's go through that slowly as we work it out. That means c squared t squared equals c squared t prime squared minus v squared t prime squared. And that means c squared t squared equals t prime squared into c squared minus v squared. Now let's divide everything by c squared. T squared equals t prime squared into c squared divided by c squared is 1 minus v squared divided by c squared. Now take the square root of both sides and t equals t prime into the square root of 1 minus v squared over c squared. And you may remember that I pointed out that this term here is the Lorentz transform. Essentially, it means that the time in one frame of reference is not necessarily the time in another frame of reference. So before we move on, let's just remind ourselves what this has shown. T is the time interval which the person in the space rocket thinks it has taken for the light to travel from here to here. T prime is the time interval that the observer on the Earth thinks it has taken the light to travel from here to here. Now obviously t prime is going to be bigger than t, and therefore what the Earth observer sees is that the clock that he is looking at seems to be moving slower than it should, because each time interval is longer than it should be. The time interval to the person in the spacecraft is only that long. The time interval to the person who is observing from the Earth is this long. And if you have longer time intervals, then the time itself will go more slowly. And that's why a moving clock moves slowly. Let's suppose, because we're going to use this in our example, that v is 3/5 of the speed of light. What then would be the relationship between the time interval for the person in the spacecraft and the time interval for the person observing that clock, but from the Earth? Well, the answer is that t equals t prime into the square root of 1 minus, well, if v is 3/5 of the speed of light, v squared over c squared will be 9 over 25. In other words, 3 over 5 all squared. And that equals t prime into the square root of, well, 1 minus 9 over 25 is 16 over 25. And the square root of 16 over 25 means that t equals t prime times 4 over 5. And that suggests that the time measured by the person in the spacecraft is 4/5 of the time that the person on the Earth thinks it ought to be. It's travelling slow. We can put this another way. We can say that if the person on the Earth, looking at the clock in the spacecraft, also has his own watch, when he looks at his own watch, he will see that 5 seconds has gone past. But when he looks at the clock in the spacecraft, he will see that only 4 seconds has gone past. Or, if 5 years have gone past on Earth, only 4 years will appear to have gone past in the spacecraft, because the moving clock in the spacecraft is going slow. Of course, as I explained in the videos on special relativity, this applies both ways. If you've got two people on, let's say, different frames of reference, and the relative speed between them is v, then when this observer looks at this person's clock, it will appear to be running slow. But equally, when this person looks at this person's clock, that too will appear to be running slow. It works both ways. So, now let's go back to the diagram, which I've drawn out a little more carefully here, of the two twins. This is time running up from 0 to 10 years, and this is distance in light years. And just to remind you, number one twin stays on the Earth for 10 years. The Earth is not moving for these purposes, And so there's no movement through space, simply a steady movement through time. And 10 years later, the twin is here in space-time. The other twin was picked up by a rocket that was travelling at 3/5 the speed of light, and that travels out for 5 years and is then transferred to a rocket that's coming back the other way at 3/5 the speed of light, and that's the line back. At which point the rocket drops the second twin off next to his twin brother, and they are supposedly going to celebrate their joint 10th birthdays. But as we shall see, that won't happen. Now why? Well, let us suppose that there is some communication between the two twins. The communication travels at the speed of light. It cannot travel faster. There can be no instantaneous communication. You cannot move from here to here, because that would suggest you were travelling infinitely fast. You were travelling a distance in no time at all. Communications must travel at their fastest at the speed of light. So let's suppose that there are some radio waves carrying picture signals. What is actually happening? Well, we're going to consider the person on the Earth receiving signals from the twin in the spacecraft. When the twin on the Earth is 2 years old, he or she will receive a signal from the spacecraft. That signal must have come from this point here, because this is the 45-degree angle that represents the speed of light. And so the twin on Earth, aged 2, will see the twin in the spacecraft, who incidentally is standing next to a clock, and what time will be shown on that clock. Well, you might read across from this chart and say that the time on Earth would be 1.25 years. But in fact, of course, we've just shown that the time on the spacecraft will be 4/5 of that. So we have to multiply this by 4/5 to get the time on the clock on the spacecraft, which will then be 1 year. So what we're saying is that when this twin is 2 years old, he or she will see a picture of their twin with the clock showing 1 year. Now what happens when the twin is 4 years old? Well, the twin will receive light that emanated at this point here. What is this point in Earth time? In Earth time, it's 2.5 years. But we have to multiply that too by 4/5, and that gives 2 years. So now what we're saying is that when the twin on the Earth is 4 years old, he or she will see a picture of their other twin with the clock showing 2 years. Now we move forward again to when this twin on Earth is 6 years old. The time on Earth will be 3.75 years. But we have to multiply that by 4/5, which comes to 3 years. Now we go forward again. What happens when the twin on Earth is 8 years old? They will receive a signal that was sent from here. That is 5 years Earth time, but multiply that by 4/5 and you get 4 years. Now we're going to go forward just 1 more year on Earth. The twin on Earth is 9 years old, and the light will have come from here, travelling at the speed of light. That is 7.75 years on Earth. But we have to multiply that by the conversion or Lorentz factor of 4/5, and that gives us 6 years. Let's just go forward by half a year. The twin on Earth is now 9.5 years old, and the light has emanated from here. That's at 8.75 years Earth time, but according to the spacecraft, that's running slow, so you have to multiply that by 4/5, and you get 7 years. Now, can we see what's happened here? When the twin on Earth was 2 years old, the picture showed the other twin 1 year old. When the twin was 4 years old, this one appeared to be 2 years old. When the twin was 6 years old, this one appeared to be 3 years old. When the twin was 8 years old, this one appeared to be 4 years old. When the twin was 9 years old, this twin appears to be 6 years old. And when this twin is 9.5 years old, this twin appears to be 7 years old. And so when the twin eventually arrives back on Earth, I think you'll see that it will be 8 years old. So when the twin that has been in the spacecraft arrives back on Earth, next to its twin, one will be 10 years old, that's the one who stayed on Earth throughout, and one will be 8 years old, that's the one who has been in the spacecraft. Now you might argue that surely that cannot be, on the basis that these things are supposed to be relativistic. Surely if one person is on Earth and the other person is moving, each of them will have the same perspective. That is to say, if we did exactly the same thing, but looking at it from the perspective of the person in the spacecraft, surely they would perceive that the clock on Earth was running slowly, and that therefore in 10 years of space travel, the clock on Earth would only advance by 8 years. But actually that is true if there was constant motion. That's special relativity. Here, something rather important has happened. At this point here, and at this point here, and at this point here, there has been an acceleration, and a pretty dramatic one at that. And those accelerations are what changes the whole perspective. The person on the Earth hasn't accelerated at all. They may have been travelling at constant velocity. There's no way of finding that out. That's what special relativity says. But you know if you've been accelerated, because in this particular case, it would probably be unsurvivable. Nonetheless, we've ignored that point. Acceleration is something, when it suddenly happens, you know. When you're sitting in a car and it suddenly accelerates forward, you are pressed back in your seat. When you're sitting on a train and the train goes forward, you go back in your seat. You know that acceleration has suddenly happened. And that's the difference. The person in the spacecraft has been subjected to acceleration, and acceleration slows clocks down. You might ask the question, what would have happened if the spacecraft had been travelling faster than 3/5 of the speed of light? Of course, it can't ever travel faster than the speed of light, but supposing it had been travelling at 4/5 the speed of light. The answer is that the twin would have aged even less in the spacecraft. The faster you go, the more your clock slows down and the less you age. I acknowledge gratefully the work done by Brian Cox and Jeff Forshaw in their splendid book, Why Does E Equals MC Squared, an excellent read and easy to follow. They have done the calculation for me. They say, let us suppose that there is a twin who stays on the Earth throughout, and there's another twin who goes in a spacecraft. Here's the twin in the spacecraft, and the spacecraft is actually not travelling at constant velocity, but accelerates at a rate which is exactly equivalent to the gravitational attraction on the surface of the Earth. And it accelerates for 10 years until it gets here. And then it decelerates at the rate of g, minus g we can say, until eventually 10 years later it stops and turns round. And then it comes back, accelerating at the rate of g for 10 years until it gets to the midpoint again, and then it decelerates at the rate of g until eventually it comes back and stops on Earth. Now, these 10 years are measured, 4 periods of 10 years, are measured by the clock on the spaceship. And so the twin in the spaceship thinks he has been away for 40 years. He has aged by 40 years. How long has passed according to a clock on the Earth? Well, this is rather more difficult to calculate because now we really are into the realms of general relativity because we're accelerating the whole time. But fortunately, Brian Cox and Jeff Forshaw have done that calculation for us, and they find that the clock on the Earth will have gone forward by a staggering, wait for it, 59,000 years. And what does this actually mean? It means that the twin who travelled out and back in 40 years will arrive back on Earth to find the Earth 59,000 years into the future. There is, however, one important downside to all of this. There's no going back. You can spend 40 years of your life in a spacecraft to arrive back on Earth to find what is going on 59,000 years into the future, where all sorts of medical advances might have happened that would give you your 40 years back and give you a much longer life perhaps. But you can never ever do the return journey. You can't go back to meet your twin, who of course 59,000 years on will long since have gone. And the final point I want to bring out for this video is that what we've shown is that when you are in an acceleration, you find that your clock will move slowly. An accelerating frame or accelerating body will have a clock that moves more slowly. And by the principle of equivalence, that means that if you're in a gravitational field, your clock will move more slowly, because you'll remember what the principle of equivalence was under the general relativity video. It is that someone who is inside a box, standing on the Earth, where they are subject to a gravitational attraction of G, even though they don't fall through the Earth, is in exactly the same position as if they were a rocket accelerating at G. And so if you're in a rocket accelerating at G and your clock slows down, it must also follow that if you are in a box in a gravitational field of value G, your clock will slow down to the same extent. So the bigger the gravitational field, the bigger the effect will be on the clock. And I leave you therefore with this idea that if you live in a block of flats, high-rise flats, the person who lives on the top floor has a slightly lower gravitational field than the person who lives on the bottom floor, because gravity will be greater at the bottom than it will be at the top. Of course, on Earth that's barely noticeable, but it will be true. And since clocks move more slowly in a bigger gravitational field, it means that the person living on the bottom floor will age more slowly than the person living on the top floor. Fortunately, on Earth, that will only be a matter of a few microseconds in a whole lifetime, so it doesn't really make that much difference. But if you do stay in a ground floor flat, at least you have the knowledge that you have the chance of living longest.